Related rates is the next thing we're going to be talking about. Okay, this is one of the more complicated things in the unit because it's basically implicit differentiation in the real world. Only instead of doing d over dx, you do d over dt. Okay, and the most classic way of teaching this, and I love teaching it this way as well, is using a ladder. Okay, for some reason they use ladders as an example for these, and it shows up on like almost every AP test. You're going to see it on a lot of tests that we have in this class. But it involves a ladder sliding down a wall. And step one for these is always to draw it out. Always, always, always draw it out. So it says the top of a 25-foot ladder is sliding down a vertical wall at a constant rate of 3 feet per minute. Okay, so here we go. Let's draw this out. So here's that wall. It's a vertical wall. Here's the ground. The ladder is going to be here. This is going to be the side view of the ladder, apparently. Okay, and this is going to be 25 feet. It's sliding down the vertical wall at a constant rate. So it's on this vertical wall here, and it's going down. Anytime I have a rate, I use an arrow. Okay, so if you're one of those people that likes vectors, it's kind of like that. It's just showing that it's moving. It's not a static thing. And it's going down by 3 feet per second. If you notice, that's 3 feet per second, and the ladder is 25 feet. One's a rate, one is not a rate. Okay, one's just a measurement. I guess they're both measurements technically. But. All right. When the top of the ladder is 7 feet from the ground, so the top of the ladder is 7 feet from the ground. So what I'm going to do here, do one of these. This is 7 feet. What is the rate of change of the distance between the bottom of the ladder? Okay, so we're basically looking for this part right here. It's going to be going that way. As you can see, the top goes down. This part is going to go out. So you can kind of just imagine it. We're looking for this rate right here. How fast is that thing moving away from the wall? You can't solve this with algebra. It'd be nice if you could, but you can't. Okay, because we're looking at instances in time. So next thing I'm going to do is, this is just everything that's given. Step 2 would be to create a related equation. So not a related rates equation, but a related equation. So what equation relates all of these measurements together? Okay, does anyone know the equation? Just yell it out. Here's a hint. Pythagorean theorem. Okay. So the next step would be, again, to create the related equation. Relate all the variables together. That will be algebra. The next step, though, is to create a related rates equation. So that means you have to ratify this. And I don't think ratify is a real word, but you're going to hear me say it a lot. You have to ratify this, and the way to ratify this is by doing the derivative with respect to time of both sides. D over dt has to go in front, by the way, so if people keep doing this where they throw it at the end, it drives me nuts. Don't do that. It makes no sense. All right, so we need to do the derivative of this. Now, the great thing about the real world is it's not as complicated as those made-up, convoluted, implicit differentiation problems. You notice this is pretty easy to do the derivatives of. So what is the derivative of a squared with respect to t? What does that simplify to? Just yell it out. 2a times dA over dt. Very good. The a and the t don't match, so you have to multiply by dA over dt every single time. Okay, all of them are the same way with this because it's, you know, b squared and c squared. All right, just for the sake of ease, I'm going to divide both sides by 2, just because it makes it really pretty. Okay. Now from here, the next step, if you notice, there is no more calculus. We are done with calculus on this problem. The rest of it is all algebra. It's just like the implicit differentiation stuff. You just need to solve for whatever we're looking for. Well, which one are we looking for here? What variable in the orange are we looking for based on the picture there? B, not B. No, that's you need B though, but what are we looking for? What does the question say? Right, so which one is that in the orange? Is it A, is it dA over dt? Is it B, is it dB over dt? Is it C, is it dC over dt? Which one? dB over dt, very good. So this right here, what we're looking for is dB over dt. That's what we're solving for. That means that everything else, you have to know it. There is some way that you should be able to figure it out or it's given. So let's go through the list and see which ones are given here. Is A given for this one? So we're right here. Is A given? Yes. It's equal to 7. Okay, 7 feet. Now, AP never tries to trick you with the units. So if you want, you don't have to put the feet in there. They're not going to like switch it to meters at the end and you have to like, you know, convert it or something like that. It does not happen, but I'm going to throw it in there for fun. Okay, dA over dt, what's that equal to? 3 feet per second. That's where it's awesome. It's dA over dt. This is a rate. This thing right here is a rate. So you can look over here at your picture and go, oh, I draw rates with arrows. There it is, and that's A. That's the rate of A. This is insane. Plus B. B is not given, but how can we find it? What? It's 24, but how can we find it? Help everyone at home here. Yep. You can use A squared plus B squared equals C squared to get that this B right here is equal to 24 feet. It's a Pythagorean triple. These problems tend to be on the calculator, or I'm sorry, non-calculator part of the test. So they usually use 3, 4, 5 triangles or any other Pythagorean triple. Yes, go. Oh, shoot, that's embarrassing. Oh, it's feet per minute. This is the worst. Sorry. Thank you for everyone. But it is definitely negative. That's really embarrassing. Okay. Feet per minute. Shouldn't have put the units in there to begin with. Okay, feet per minute. Okay, and it is negative. Thank you, Hunter. Okay, and that is important. You definitely have to have that in there. All right, B is equal to 24 feet. dB over dt is what we're looking for, so I'm just going to write dB over dt. C is equal to 25 feet. And then what is dC over dt here? Who said that? Why is it 0? It's not changing. Why do you think 1?
I thought 1 because it's constant.
Well, if it's constant, it's not changing. If it's not changing, then the rate of change is 0. Very good job. Sometimes that's the most confusing part. They're like, dC over dt, that's not given. Well, the ladder, it doesn't say it's shrinking or growing or anything like that. It should probably say that it's a static ladder, but I guess you just kind of have to assume that. Anyway, this is 0. Now the rest of it is just filling in everything that we know. That's a negative plus 24 feet times dB over dt is equal to 0. All right, I'm going to add the 21 feet squared per minute to the other side and then divide by 24. So you're going to get, I guess I can divide both sides by 3 here really quick too. So negative 7 and 8. So it's going to be 7 over 8, and it's 7 feet squared per minute divided by feet. You notice the units work out the way they're supposed to. (7/8) feet per minute. Now, say I didn't make that negative 3. You would just have a negative 7/8 feet per minute. But you should notice that the rate is actually going positive. So it's one of those, you really understand the problem as a whole, then you can kind of notice when, if you mix something up like that with the negatives. Okay. Questions on that one? Okay. As one thing changes, another thing changes. The rate of one thing affects the rate of another thing. Okay. Now you can do this with anything. You can do this with circles. You can do this with spheres. You can do this with cylinders. You can do it with anything that one thing changes, the other thing changes. You know, one way of thinking about this too is if you're gonna be an engineer, like if you're building a bridge, if there is a temperature change, then the bridge changes its length, whether it's expanding or contracting based on the temperature change. So one rate is related to another rate. That all has to be calculated. Otherwise, you're building a bridge and then all of a sudden it falls down because you didn't take into account how certain rates affect other rates. Okay, that's just an example for any. I can think of a million things for any STEM-related field where you would use this. Okay, in chemistry, if you've taken AP Chem, you have to do reaction rates. Eventually, reaction rates are instantaneous reaction rates, where you have to use calculus to actually solve them. If you take, I believe it's PChem, thermodynamics, basically in college, you'll be doing stuff like that. You'll be looking at those rates. Because if you are creating some chemical reaction in some factory and it produces some other rate of some other gas that's created, and you didn't make the machinery designed for that well enough, then maybe there's going to be some explosion because there's a buildup of pressure or something else that happens. All that stuff has to be accounted for and calculated before you create anything. Okay, you don't want to just start building a factory and go, man, I hope this works. That's how someone gets hurt or dies or anything like that. All that stuff has to be accounted for ahead of time. If you've seen the movie Hidden Figures, they break down all the math that has to be calculated before you send someone up to space, because if the math is right, then maybe it's going to be a little bit more safe. Okay, and there's certain rates of change for that. If you go too fast in the rocket, then the blood in your brain is going to go all the way to the back, because they're usually facing like that when they go up. People at home don't know what I'm talking about, or maybe you can see me. I don't know. But if you don't account for that, then the person just blacks out or dies, right? Because the acceleration was too fast. What else? In business, I invest a lot in diversified funds. If you're not supposed to really follow one stock versus the other, you want to follow a bunch of things. But it's awesome if you do it correctly, and computers do a lot of this stuff, where if you invest your money into something that grows, and then also invest it into something that, even if, say, the one thing that you invested in goes down, the other thing isn't affected by it. Sometimes stocks are related, where if one goes up, the other one goes down, or if one goes down, the other one goes up. You want one where they're not affected, they're not related to each other, because that way one can go up and the other one's not, or say one goes down, the other one's not affected by it, you'll still make money. Okay, if you invest in the stock market the right way, like more low risk stuff, you'll gain about 9% every year. And that's because if you do diversified funds. That's why this whole GameStop thing that everyone's going for, like, oh man, people are billionaires, people are making a bunch of money. It's almost like a Ponzi scheme, if you know what that is. Okay, so you're causing a bunch of people to change the rate of buying it so the stock price goes super high. And that's awesome if you bought it super low and the stock price goes high, and then you could sell it. But some people are buying it so late, they're buying it when it's $400, and then the stock drops to 100. Now you just lost a ton of money because you didn't take it into account, because it's just one stock. You want to diversify as much as possible. That way, if one thing changes, it doesn't mess up the whole thing, if that makes any sense. That's business. What else? I already talked about engineering. And I just use bridges because I don't know anything about engineering. That's always the example that I use, but it could be for building anything, really. I don't know. This is hugely important. It's the main reason why it's covered in calc, and why people that are going to be engineers have to study this, because one thing changes, another thing changes every single time. That's the main thing. You can't do that with algebra. Let's see what else do I want to talk about. I think that's it for that one. Okay, these are difficult. You cannot practice these too much. Okay, so if you go to the website, you'll see a ton of those problems. Good to do. You can just do the derivative of each equation to get to the next one.